Hello everyone, and welcome to my presentation on how a tiny head detector powers intelligent video conferencing. So, part 1, necessary beginnings. This story starts back in late 2018, when I was just a bright-eyed computer science student doing an exchange year in Australia. And honestly, I wouldn't enter this story until half a decade later. No. Still in 2018, but the story starts in the Cisco office in Oslo, where smart people have been making video conferencing devices for some decades now. And we make all kinds of video conferencing devices. We've got codecs, fully fledged systems with cameras and microphone arrays, touch panels, desk devices, pan, tilt, zoom cameras. We've got stuff outside the room, and we've got stuff inside the room for big rooms and for small rooms. And in this particular office, at this particular point in time, my future colleague, Christian, had a problem. But the thing is, it just wasn't his fault. Remember, we're doing video conferencing here. So let's say you joined a meeting, and this is what you see on the far end. And in a large meeting room like this, you might struggle to see the person in the back. Especially when considering that in practice, you're probably looking at something like this, where there's multiple meeting rooms or people joining the meeting at the same time. Now, you could zoom in, but do you want to manually control the cameras in your meetings? No, I didn't think so. So if someone starts speaking in the back, you can probably hear them, but you can't really see them. And therein lies the heart of smart automatic framing. So what do we need to do this? Well, firstly, we need to know where the person's speaking, where their audio is coming from. And if you have calibrated microphone arrays, you can audio triangulate with some good old mathematics by looking at the time difference between the audio hitting different microphones. But we also need to know where are all the people in the image to know what to frame. And for that, we need machine learning, and that's why we're here. Now, getting a person detector is something that we needed then. This auto-framing work started back in 2013, and that was a time when ML was really making waves in computer vision. And it's important to remember that it is almost always the worst solution to a problem. Sometimes it's just the only one that you have. And the fact of the matter is that there is no good way to detect people without machine learning, so it provides a lot of value. Now, back then, we had acquired this model from a third party, and it was detecting face and upper body, something like this. Now, a person detection model completely changed what we could do automatically with cameras in a meeting room. And this was the key to dynamically frame different things in the room depending on what was going on. For example, if you want a closer view of the people in the room, you can do something like this, less wasted space. And if the person in the back starts speaking, you could frame them individually, or maybe present a more equal view with both of the participants. Of course, the people sitting in the room shouldn't be aware of all of this. The idea is that they can just communicate normally, and hopefully the far end gets a decent experience. Now, automatic framing, or which is typically called the Detector in-house, was a big step forward in our meetings, but sometimes it performed poorly. You see, it relied on that person detection model, and it just wasn't very reliable. And since the model was third-party, we had very little control over it. And when the framing was poor, you can guess who took the blame. That was Christian. So, what to do? Complaining alone doesn't get us very far. We had a new system coming out, and we really wanted to do better. But Christian had seen some cool videos on YouTube, and he was sure he could do better. But not on the camera director side. He had exhausted his bag of tricks to provide a stable experience. No, the problem was the machine learning model. So, could we just make our own? you'd need some pretty good justification to start a task like that. So he devised a demo to show exactly what he was working with when trying to automatically frame. It looks something like this. This is the information that you're working with, the outputs of the machine learning model. So you have a person speaking here, and you want to frame them, right? And, well, that was awkward. And maybe you have a person here, and you're sure there's a person there, so we can frame them. And then you get audio from somewhat the same direction, slightly. There's no other person there, right? So you're still framing the wrong person while someone else is talking. That's not ideal. Or maybe you just want a good overview shot of the room, of these people here. And now you forgot someone. So, although you would want an output that looks something like this, in practice, you were probably dealing with something that looked more like this. So, to automatically frame in a scenario like this, you have to choose between either a very unreactive experience or a very unstable experience. So, I am sorry, but here's a silly haiku for you. Features sprouting from a machine learning model wobble with the base. Yeah, sorry, I'll stay away from the poetry. 2018 was the time when YOLO v3, or You Only Look Once, was coming out. And for those who aren't familiar with it, I know it's a silly name, but the outputs and the results are anything but. The results actually were very impressive for the time. And what this is an object detector that's single stage. You pass the image through the model, and it predicts everything in the image all at the same time. All the objects, bounding boxes around them, and then what they are. It was very fast, and that made it very tempting for edge devices like ours. So could we start from there? I mean, the implementation is open source. But what should we predict? We had that concept of a face and upper body detector, but we don't need to do that. Let's consider what we want. We want something that's visible on a person. We want to frame, regardless of their posture. We wanted to tell us where to frame. And yeah, a bit early on the spoiler there, but yes, heads. Heads are what we want. They're also consistently sized, very easy to label, and it's a simple concept, but for what we need it's good enough. So we want something like this. Well, this is where I should probably continue, but instead I'm going to talk about a 7-year-old AI model, as you do. So, YOLO-style object detectors are typically convolutional models, and there are a lot of architectural choices that go into how the image is processed, but I don't think that's all that interesting to discuss. I think the most important thing to talk about are the outputs of the model, because those define what you can do with the model and how you run it. So let's assume we've trained a YOLO-style object detector to predict animal heads. To understand the outputs, you can imagine you divide the input image into a grid like this, and I like thinking about the center point in the image of each of these grid cells. Now, each of these points will now all at once predict multiple things at the same time. Firstly, how confident are we that there is something of interest around here? And that'll be a number between 0 and 1. Now we can color code that so it's a bit nicer to look at and just filter out the red ones. They're still predicted, but they're not that interesting to discuss. But these points don't match the heads we want to predict perfectly. So how do you get that? Well, you want a bounding box, and you start with an offset from your point to the bounding box. So the model is predicting the offset relative to each point and to the center of an object of interest. And from there, you just need a... I'm filtering out duplicates here. That's typically done post-processing, but it's much easier to visualize if we do it now. We get a width and a height for the bounding box. And finally, what object detectors typically do is tell you what are they predicting. So in this case, it might be dog, cat, owl, or human. But it's also important to notice that it's still predicting something for all of those red cells that I filtered out before. And then you might say, that doesn't make sense. If there's no object there, what box am I predicting? What object type am I predicting? And the answer is that it just doesn't matter. For inference or for training, we just disregard it, and that's fine. But we're not trying to predict animal heads in meeting rooms. We're interested in people. We want a head detection model, and we don't really care about this object class thing. But there is something we need. We needed some head pose information, because that previous face detection model we had some inbuilt information about the orientation of a head. And we used that, for example, to nicely place a person in a frame. You can see it looks a lot better when there's a little bit of room in front of your face than otherwise. So we didn't need the object class, but what if we just make up a concept where different orientations of a head are their own kind of object and predict that? And that's what we went with, or Christian went with at the time. And it honestly worked quite well. It was good enough for the existing features. It slots perfectly into the existing YOLO design. We're still pretending to be a normal object detector. The outputs are just the same. And it's very easy to label by hand, which is important when you want to kickstart a project like this. So let's say we have an imaginary checklist now. Find a fast and good replacement for the person detector. Done. Adapt the predictions to our needs. Yeah, let's find heads. Does it run fast enough for us to run it all the time during meetings? Not quite. What if we go for the smallest model available? Not yet. What if we make it even smaller than that? There we go. Gather and label in-domain data. It's not exactly entertaining to do, but still a solvable challenge. Find replacement for the pose information. We made up that pose class concept. And now, is it better than the old model? Absolutely, by a long shot. So, we done? Well, the new model was substantially better, so Christian could just hand his model over to another internal machine learning team and go back to his actual work of doing automatic framing and camera intelligence. This time with a better person detector. And no, we're not quite done yet. We're on to part 2. Living on the edge. It's hard to compile a complete list of features that use the head detection model these days. It's just become so integral to the devices. But here's a little list that's an attempt to do just that. But as I so poetically phrased earlier, any feature that is based on a machine learning model will inherit its instability. And it tells you something about a model when such features are seemingly stable. But why is it so useful? Why is it used so much? Well, it turns out that knowing accurate real-time information about where people are in a room is just very useful for video conferencing. And the more the model is used, the higher the return on improving the model and expanding what it can do. And although the primary function of the model was to enable this automatic framing concept, and that keeps evolving to this day, there's other sort of less obvious use cases that have come up for it. Like presence detection. You can run the device even when there's no meeting going on. And if there's a person in the room, you can display that sort of visually with a red light so that a person that's looking for an available room can sort of see that at a glance. And you can define this concept called a meeting zone, where you just put in a 3D meeting zone in one of your touch panels, and it functions such that anything that happens outside of that meeting zone is disregarded. Now, someone might point out, you don't get 3D outputs from object detectors, so how are you pulling that off? Well, we found out that distance is useful to know. So here's a little puzzle for you. These are objects. Which one is the furthest away? You might think so, but you don't know what object this is. It might be anything. So it's impossible as of now. What about the most distant giraffe? No? So giraffes come in all shapes and sizes, and their posture can drastically change what this bounding box looks like. So this is an impossible task. But context matters. Given that this is a meeting room with people in it, and the bounding boxes represent heads, which heads are the furthest away? It's pretty easy. It's the ones in the center, the green and the red one. Why is it so easy? Well, it's because heads have this nice property where they're somewhat similarly shaped no matter from which angle you look at them and between people. And there's also not a large distribution in head sizes generally. So we can do a lot better than saying furthest or smallest. We also know the camera intrinsics that we're working with. We run on our own hardware. And that means that we can figure out the distance from the camera to each of these objects. Not perfectly, but quite well. And that means that we can map each of these heads to a 3D coordinate in the room. And that obviously opens up even more use cases for such a model. And this also explains why it's useful for us to find heads in particular and not full bodies. Your body can have different poses which will change the box size, and you won't see all of it at once. But head sizes are nicely consistent. Now there's more, but I don't think I have time for too many more features for now, and I was going to talk about running on edge devices. And that has a lot of challenges and upsides to it. Firstly, on the challenge side is compute. We have to make do with a very small, fast model. But why? I mean, some people have to deal with edge devices that are very underpowered, but ours are fairly powerful. Sure, we want to support older hardware, but that's not it. It's really about being a nice neighbor. You see, what you need to consider is that head detection is just a building block in a bigger system. And for all of my self-importance, the stuff I do is useful, but it's not exactly mission critical. We're running on video conferencing devices, not object detection devices, and those devices have some video conferencing to do. Okay, sure, you might say, but how much do these devices actually need to do? Well, the codec needs to run up to 3 4K screens at the same time, sample audio from dozens of microphones, do noise cancellation, decide how to frame with multiple cameras, undistort the video, encode and send video and audio, decode up to 25 incoming video streams, display the incoming video on the screens, etc. Basically, the codec is busy. And yeah, here's a non-exhaustive list in case you were distracted by my silly animations. And all of this is happening in real time, and it's very sensitive to delays and instability. If you're in a video call and you have laggy video, or God forbid, choppy audio, then the whole experience is just crap. The GPU just has a lot on its plate, and we have to make sure that we run as quickly as possible and then just get the hell out of the way. Now, a little side note, sometimes on some of our newer devices, we can run on something called a DLA, called a deep learning accelerator. Those are nice not because they're super fast, but because no one else is using them, so we can run all on our own. On to the benefits of running on edge devices, and there's plenty of those. To start with, we are as close to the source of data as possible. We don't need to send the image somewhere, process it, and send the results back. We just run it on it run on it where it is. We know exactly what hardware we're on, what other requirements the device has, how often the model needs to run, and what scenarios the model is used in. We can specialize to be very fast and very performant, specifically on our hardware and on our cameras. In a way, it's cheaper. There's no servers to maintain. The device is self-sufficient in this manner. And there's an aspect of security. We don't have to send the video or images from your meeting to some server to be processed. We can just do it on the device itself. Though, for me personally, the biggest benefit of running on edge devices is the challenge of it. You see, it is very fun to solve a problem in a constrained scenario. And running on edge devices sidesteps that dreaded trump card of AI model development, which is that bigger plus more data equals better. Sure, that may be true in a lot of settings, most settings maybe, but it's not exactly interesting from an engineering standpoint. So, no can do. Now I can read some research and find more interesting ways to improve our models. Hey, look, we reached the edge of part 2. So let's dive right into part 3. The curious case of continuous pose estimation. Half a decade has passed now. Let's see if we can inject me into the story. Don't look away. Hey, look, that's me. And we've been handed a great narrative tool, repetition. We again have an overly confident, slightly annoyed engineer. He's working on auto-framing in camera intelligence. And the model outputs he's working with just aren't good enough. See, at the time I was working on this concept called cross-view, where you have a meeting room like that and you have multiple camera angles into the same room. And my job was to figure out which cameras to use when framing that scene. And the most important thing about that is knowing which way the people are facing that you're interested in framing. There's more to it, but that's the most important part. And if you remember that post-class concept I mentioned earlier, I did know something about the orientation of the people, but it just wasn't very detailed. It wasn't very good. You see, post classes aren't very accurate. You can see that the leftmost and the middle image aren't the same, but they belong to the same class. So the angle you get from this class would be the same, 0 degrees. Whereas the third image is half left, or 45 degrees. So minimal head movement could either be undetectable or change the pose by 45 degrees. And you can imagine in a scene, if you're somewhat in between two classes, we would flip-flop a lot between them, and we can't be very reactive to head movements of people. There was also the problem of the dreaded other class. And that sort of encompassed very many different poses which didn't fit into any of the other 5 categories. But knowing that something is in the other class doesn't really tell me anything about the posture of the face. So, not knowing the history that I've been telling you in part 1, and not having worked on the head detection model before, I started asking some questions like, why is it like that? And why isn't it better? To which the answers were largely, it was easy to do at the time, and pose was largely an afterthought. So, after having worked on this cross-view framing stuff for a while, I moved into the machine learning team and started working on that. And this pose frustration from before really sat with me still. And it's something that I really wanted to tackle. But then I have to define, what do I actually want from that model? Well, we already had this pose class concept, but I wanted something more continuous. And the first thing I thought of was, well, you can have like a continuous angle So here, instead of just saying half right, this is 52 degrees off center. And you can see that there's more information in that, and you can be more reactive in that sense. But it doesn't capture the tilt and roll of the head at all, and would still be stuck with that other class for the more extreme poses. Now, the best thing would, of course, be to get a complete 3D representation of the head that captures any movement that you might see from the head. And you could maybe do some new stuff with that, like compensate for cameras that are mounted high or low, or I don't know, some other features. It's not really my job to come up with those, just develop the models. So this is where you start looking into the research. Has anyone else solved this better? And there's plenty of very interesting stuff in the research, but a lot of it is very frontal head focused. You have face key points and face recognition and stuff. And it makes sense because you have a lot of devices where you have a front-facing camera close to a face, like a phone or a laptop, web camera, etc. But we had already learned that a frontal-only view isn't good enough for us. We'd given up on the face detector before. And after some digging, we found a lot of interesting stuff, and this was probably the most influential paper for us. Now, it would be very funny if one of the authors were in the audience, but I won't get my hopes up. No? No, okay. It would have been very funny, though. Anyways, toward robust and unconstrained full range of rotation head pose estimation. And they had trained some models where the input was the crop of a single head, and the output was complete pose estimation for any orientation of that head. Also the non-frontal poses, which was very uncommon amongst the papers we found. And they got some very impressive performance due to a smart choice of how they represent 3D orientation of a head. And this really struck home with me, because I had been very frustrated with how we represented pose. And this paper put a very large emphasis on exactly how you represent it. But how might you represent the orientation of a head? Well, the first thing most people would think of is Euler angles, very common for cameras, for example, where you have pan, tilt up and down, and roll to the sides. And those are neat. It's only 3 numbers that you have to keep track of, but they suffer from a number of problems as well. If you know what a gimbal lock is, you know that is a problem. There are many ways to represent the same orientation, which can be problematic when training a machine learning model. It's best that you can nudge the model towards one right answer. And Euler angles can look very different, even though they represent an orientation that is very similar, which is the case with the Euler angles on the paper screenshot there. Quaternions are another alternative. They're popular in some groups, but not exactly a lightweight concept to explain. You get geek points if you know what they are, but I won't try to explain them. Rotation matrix is what the researchers ended up going with. And that seems kind of big and scary. It's 9 numbers and it's a matrix. What is it really? So it's just 3 vectors. They're orthogonal and they're normalized. And to understand exactly what they are, each of the vectors in the matrix over there are color-coded to match the lines that I've drawn on the face. So it's fairly intuitive to understand exactly what it does when you see it like that. So you want the model to predict a rotation matrix like this, but then you have to force the model to predict something that's orthogonal and normalized. The model might spit out something that's completely different. And then you have to post-process that to somehow be orthogonal and normalized, because a rotation matrix doesn't make sense unless it is. And the easiest solution to that is just skip one vector. If you predict 2 vectors freely, you can reconstruct 3 orthonormal, so orthogonal and normalized vectors from that with something called the Gram-Schmidt process. And that means the model doesn't have to bother with learning to predict something that is orthogonal. We can just do it for it. And this process is deterministic as well. And what's really nice about this rotation matrix is that there is a one-to-one mapping between a rotation matrix and the orientation of a head. You see, there is only one correct rotation matrix for each head rotation. And for each head rotation, there is only one correct rotation matrix. It turns out that the representation matters a lot. If you train the same model in the same way, but just change the way that you expect the model to output rotation, then you get different results. If you train with Euler angles, you end up here, close to 8 degrees. Quaternions, a little better. Train on the full 9-number 3-vector rotation matrix, gets better. Deconstruct it to the 2-vector 6-number version that where you reconstruct the rotation matrix, even better. And then if you use a geodesic loss on top of that, you do even better. Now, geodesic loss may sound kind of scary, but just imagine you have 2 vectors, you predicted the red, you wanted to do the green. You want to see how poorly you did. So you might look at a Euclidean loss, so the straight distance between the two. Or you might do a geodesic loss. And considering that we're working with angles, the geodesic loss just makes more sense in this case. And so the model performs better. By the way, did someone else look at that and think, ice cream? Yeah? I think so. Anyways, we've concluded that the representation is very important. But just how bad then are those pose classes that we had? Well, someone might say, but you have an object detector. An object detector predicts confidence and bounding box and object classes. What are you going to do with that fancy rotation matrix stuff? Well, sure, confidence, bounding box, and an object class is typically what you would output from an object detector, because it's a useful thing to predict objects. But there's no law of nature forcing you to predict exactly these things. The beautiful thing in machine learning is just how flexible it can be. And originally, we had retained that same output structure as a standard YOLO object detector just because it was the easiest thing to do. But we could really predict anything. Now, as long as you have labels and some way of matching that label to predictions, machine learning models can just adapt to any output you throw at them, or any label you throw at them. So what do you want to predict? I mean, you're already predicting a head and something about the head, as the pose class. You might as well try something like eye color, ear size, number of arms on the table, distance to the nearest door, or even a rotation matrix representing the rotation of the head. A little caveat there is that if you want your model to do different things, it helps that when they are related. Most of the weights are shared, so if you have very different tasks, the model might struggle to learn both of your tasks at the same time. But before we continue, do I really expect this to work? Let's compare what we have. We've already found that we have some research models that can pull this off to a pretty good degree, that is predicting the full 3D rotation of a head. But these models, they need pre-cropped heads, and they process one head at a time. They don't have to deal with bananas or chairs or tables. They only see heads. And they process them one at a time. So if you have a meeting room like this, our whole device would just crash while trying to go through 50 different detections. On the other hand, we have our model, which has to detect all the heads in the image all at the same time and predict pose for each of them while it's at it. The research models we found were upwards of 30 million parameters in size, whereas we're dealing with less than 2. They're also trained on large research-only datasets, and we have our own, although very in domain and useful to us, smaller dataset. And an important thing as well is that we cannot sacrifice head detection performance to do this. There are so many features that build on top of the head detection model that having any kind of regression there is just out of the question. But we also don't need to be perfect. We don't need to be the very best that ever was Poe's prediction model. We just need something that is useful. Now, do we have unrealistic expectations here? I didn't really think so, and there's some reasons for that. We had already figured out that head detector could learn both heads and Poe's classes at the same time, so some measure of Poe's. And through other experimentation, we've also found out that it can do other things at the same time, as long as they're somewhat similar. And conceptually, understanding what a head is and understanding the rotation of a head isn't that far off from one another. We've also learned that for the model to learn Poe's classes wasn't all that difficult. We would typically weigh down that task during training. So that's enough theorizing. I basically joined forces with another engineer in the machine learning team, and we decided to give it a go. And you can imagine some cool compilation of what was going on over those 2 or 3 months, and then we got results. Firstly, Poe's. The 3D Poe's predictions looked pretty good. And the fascinating thing was that even after converting that full 3D Poe's representation back to the discrete angles that the Poe's classes were predicting before, we were still better compared to the model that was predicting those classes outright. What about head detection? Well, we saw slight improvement in performance there. But how? Why? What's the catch? Isn't learning this 3D Poe's concept more difficult? Well, the only thing we did was replace that class concept with a dense rotation matrix as the paper and use that geodesic loss. We hadn't changed the model size at all. That means there was no change in inference speed at all. We hadn't collected any new data. We just updated our existing data set with a better representation of Poe's, this continuous one. And we hadn't changed the way we trained. So, did we get this for free? Well, here's my intuition for why, though you can take that with a grain of salt. This is, after all, machine learning, where everyone is guessing and no one knows what is going on. So, my intuition is that classes were a poor learning objective for Poe's. They make a lot of sense for predicting different kinds of objects, chairs, tables, elephants. But they completely lack the smoothness that you want to predict something that is really continual in nature, like the orientation of a head. If the model predicted frontal or 0 degrees for that head on the left, then that is as good as it gets. You can't nudge it to become better. It's perfect. Whereas if it predicted frontal on the head on the right, it would be completely wrong, even though those orientations aren't very far from one another. There's a complete lack of nuance in the predictions. So I think that the same lack of smoothness that annoyed me when I was trying to use that Poe's information to do the multi-camera cross-view thing was probably hindering the model as well. And there's the fact that just slight movement can suddenly change the class that is correct to predict. On the other hand, a rotation matrix is a good learning objective for Poe's. If you have slight movements of the head, you'll get a slight change in output. It's fairly compact, it's smooth and continuous, There's a one-to-one mapping between the rotation matrix and the head orientation, and it handles tilt and roll as well. And these are outputs from our actual model. So why could head detector replace pose classes with three-dimensional pose, despite that being a much more difficult task? It's because pose classes are an easy task, but a poor learning objective. Whereas pose vectors are a hard task, but a good learning objective. And even if I'm wrong, the model sort of speaks for itself and is useful. So there's that. And that was the case for a curious pose, the curious case of 3D pose estimation for free. But a little side note there, this is typically how we improve our model, whether that is becoming better at something we're already doing or figuring out something completely new for it to do. There's just so many high-quality papers out there, and it's just a matter of finding something that's relevant for us and then testing it out while adapting it to our specific case. It's not always, we don't always get the same results, but it's often worth trying. Something we have learned, though, is that research runtime benchmarks just aren't necessarily relevant for us. You might have papers that say that they went significantly down in parameters and floating point operations and got some great results. And then we try them, and that's true. The other day we halved the number of parameters of a model and maintained the same scores. But we also ran more than 10 times slower on our actual hardware. So there's keeping that in mind. Anyways, part 4. I promise I'm done soon. Shower thoughts. So we've come a long way in this presentation, but I was more thinking of in terms of computer vision. It's not that long since computers were laughably bad at just about any vision task. It really only picked up around 2012 with AlexNet, and even that was just doing classification. Then you were still a year or two away from even the more rudimentary object detectors. So, a detection model in 2025? I honestly think that small, specialized, discriminative models like our head detectors are more relevant than ever. And they're becoming better and more versatile every year. And I find them amazing, but I'm a computer scientist and a nerd. Their outputs may not look awe-inspiring to everyone. And I don't think they ever were, even when they were new. So let's cycle back to that year 2012. What could computers do in 2012? Fully animate beautiful movies like Toy Story 3. You could play realistic computer games without lag. They could destroy humans at chess and run the whole internet. And while this is happening, computer vision researchers are talking about this scientific breakthrough because they can differentiate between a coffee cup and an elephant most of the time. That doesn't sound very impressive, does it? My 1-year-old can do that. So discriminative computer vision models are doing these things like classification and bounding boxes or even segmentation. And are they difficult? Absolutely. For computers, if you know how you do this, this is very impressive stuff. But they're still trivially solvable by a toddler. And I think that just makes it less impressive to us humans. Although, speaking from experience, they are much less maintenance than a toddler, and therein lies their usefulness. Now, I think computer vision AI has been solving tasks that normal people outside of the field probably just expected computers to be able to do already. They're also typically just a building block in a different system. They don't do anything on their own. They provide some useful information that some system can use to do something. Let's contrast that with generative models. These models are, at least sometimes, very impressive, all on their own. They enable us to do new things like speeding up existing tasks or either do new things or speeding up existing tasks. They can help us with writing, for programming, or generating silly images for a presentation. And that makes them directly useful almost all on their own. And I think that's just more impressive to us humans than boxes that a toddler can draw. But despite not looking flashy, I think that what computer vision models have been doing for the past 13 years has been revolutionary. But it didn't really happen overnight. But as they've been maturing, they've made their way into all kinds of industries. They're almost everywhere. They're in farming, they're in manufacturing, they're in groceries, semi-autonomous driving, robotics, and yes, even video conferencing. They're extremely fast, scalable, and cheap, perform even in limited situations, and sure, they're not perfect like anything you do in machine learning, but they're often so good that they can operate completely without human supervision. They're simply useful. Anyways, here's some fun facts to leave you with. The sun is about 1.3 million times larger than the Earth in volume. GPT-4 is about 1 million times larger than our head detector in number of parameters. And I think in that regard, it's fascinating what people have been able to do with these massive models, how they can scale them up to this size and what they can do. But I think it's also fascinating what we can do with tiny specialized models. And that's everything.